This is the lecture Artificial Neural Networks in Python from scratch. And some scratch means I really want to show you step by step, line by line, how to create an artificial neural network in Python. The target audience of this lecture are those people who just have started learning about artificial neural networks and maybe have some basic programming experience, preferentially in Python, and who really want to know how these networks work. And therefore, I set up this lecture and divided it in two main parts. Of course, I'm going to start with an introduction, but the first part of the lecture, which I call the core, is about creating a single neuron. Then I want to show you how to create a layer of neurons and then different layers of neurons. I want to talk with you about so-called activation functions, then softmax layers. And I also want to show what loss and entropy has to do with a neural network. And then I want to show you what backpropagation is and optimization. These two parts, so backpropagation, optimization, enable a neural network to learn. And also want to show you how to train a neural network and how the actual learning process works. And after that, we're going to have a fully functional neural network. And I call it the core because we're going to use this as base for other neural networks and other architectures and structures. So for example, we want to continue then with a so-called convolutional neural network, or CNN, where we will use this core. And in other lectures, I will show you how to use this core for an RNN, an LSTM, and I also want to show you how the architecture, for example, of a transformer works. And for the convolutional neural network, of course, I want to show you how convolution works and what convolution actually is. Then I want to talk with you about pooling, the sigmoid function, flattening. Again, we have to talk about backpropagation. And of course, we are going to test the artificial neural network, the CNN then, and I want to make some final remarks about the training process, so common pitfalls, and how do you have to set up the training sample, and many other things. But let me first introduce what a neural network actually is and why we need to talk about artificial neural networks. The first time they have been applied successfully actually was in terms of image processing. And what you see here, for example, is an image segmented into different regions, and also here as well. And these images have been generated from neural networks which have been trained to distinguish, for example, a person here from the background where you see those buildings, the sky, or also the street. And you can also use this, for example, for autonomous driving, or here for in medical science for diagnosing diseases or so. And that's been done for the last 15, even 20 years. And also artificial neural networks can be used for language processing, for example, for translating from one language to another one. And you can also combine this with image processing, for example, writing or setting up an artificial neural network that describes what it sees in an image. So that's called image to text, or also video to text, and vice versa. And it also played a role during the pandemic a few years ago when it was about monitoring social distancing. And I also want to show you an example from life science, because there's an example where it really had a huge impact. So the software that came up was AlphaFold, and that essentially is an artificial neural network that can predict a very complicated 3D structure of a protein. So they're usually way more complicated, what you see here on the right-hand side, just based on the sequence of amino acids. And that actually usually requires lots of effort. So first of all, you need to have a sample, you have to prepare the sample, you need an electron microscope to take images, and then you have a huge pipeline of image processing. And that really takes days, if not weeks, and you need an entire laboratory for that. And this software, AlphaFold, can do the whole process just within a few minutes. And so you can imagine that it really had a huge impact in the life science community, especially structural biology. And you probably know also JetGPT, which is a language model, and language models have been there for many decades, but they haven't been very successful. But a few years ago, people came up with this particular architecture, which is called transformer, and some underlying mathematical rules or concepts like cross-attention, self-attention. And altogether, this enables this network to understand, in quotes, of course, something like context. And in the same idea, more or less, you can generate AI art, and you probably also have came across with AI art. So there are many reasons why we should learn how such an artificial neural network works, and therefore we want to create a simple but fully functional convolution neural network in Python. And we don't want to use any external ANN related library. So we only want to do this with NumPy. Of course, we're also going to use matplotlib and maybe a library for displaying an image or something, but we will not use an external library that is somehow related to artificial neural networks. Of course, there are lots of libraries available in Python and also in MATLAB, and they're extremely user-friendly and fully optimized. And they are just perfect, and I have been using them many times. But they're still like black boxes. And the idea of this lecture is that if we can really build it, then we actually understand it, so that we really understand the foundations of these networks. How do they actually work? And that's, of course, is a very valuable skill set. And also, I find it pretty interesting anyways, how they actually work. And it's also nice to see that somewhat, let's say, abstract math then turns to actual code. So we will talk about the underlying mathematical principles. And for example, when we talk about these different training processes and we're going to change a bit our mathematical model, then we see how it will improve the performance in training, for example, or speeds up the code. So we'll, of course, talk about the underlying mathematical rules for this network. And at the end, our code will not be very fast, will not be optimized concerning runtime. And of course, we want to have a nice graphical interface. It's really about the basics and understand the very basics that we have a fully functional network. The good news is that it doesn't require lots of math. So actually, high school math is fully sufficient. So we have to talk about derivatives, for example, especially when it's about backpropagation. Then we will talk about derivatives quite a lot, and I will show you the equations, of course, and introduce that a bit. Then we only need basic linear algebra, like the dot product, so how we multiply two vectors or two matrices, and also mean and variance. And you only need very basic knowledge in Python. And even if you haven't worked with Python yet, if you, for example, have worked with MATLAB or Octave, you will see that the syntax is pretty similar. And if there's any particular difference, which you only have in Python, of course, I'm going to show you that and discuss this a bit. Nevertheless, I will provide some introductory courses, both for Python and MATLAB. So if you want to see those first, please do it. But as I said, for this course, you only need very basic programming knowledge, and I will explain everything step by step. So we will really start off very simple and then gradually improve our code. This lecture has been inspired by this textbook, Neural Networks from Scratch in Python by Harrison Kinsley and Daniel Kukila. Especially the first part is really based on this book. I applied some modifications. So for example, I extended a bit the part about math. So I will discuss the mathematical background in a bit more detail. But it's an amazing book. So I really recommend to read this book in parallel to the course. And this is really my personal opinion. So it's not an ad, and I'm not getting paid for that. So it's really an excellent book, and I would really recommend to use it in parallel. And the second part, of course, is, so the second part will be a bit different when we create or build a convolutional neural network, which is not part of this book. But the first part, which I call the core here in the lecture, is really inspired by this book, and I will use the same notations for the variables and for the functions so that you can really read this in parallel. All right, so then let's actually start with our first step, and let's take this first step and create a single neuron. So first of all, what is the idea? So people were thinking about artificial neural networks already in the late 50s and also in the early 60s. And we want to take a look at this problem from a very conceptual and abstract point of view. So what we have here in a biological neuron, so to say, is that we have inputs and they somehow generate an output. And at the time, people, of course, didn't know what's going on there biologically, biochemically. And we also don't really know that. And even today, we don't really know that. And we don't need to know that because we really want to see this from a conceptual point of view. So we have some inputs that enter the neuron. Something mysterious happens inside, but it generates an output. But if we want to write this as a code, and if we want this neuron and also the network being able to learn, how should we model that? And the first idea is that those inputs have to be weighted somehow. So we have to multiply these inputs with some weights in order to distinguish between important and unimportant inputs. And that's what the network has to learn. And that's the actual learning process. So it's just changing and adjusting those weights according to the desired output. So just imagine the network has some external stimuli and has to respond to that in an appropriate way. So it kind of has to learn that. So therefore, it has to distinguish what is important input and which input is not important. So for example, if you multiply an input with 0, it will not contribute to the overall output. So this weight is 0, and if you multiply this with a large number, with a large value, it will contribute a lot to the output, and we have to adjust these weights. And in principle, you can see this as the memory of the network. So after it learned, it knows how to respond to an external stimulus, and this is the entire learning process. And the output, therefore, is something like the sum of the weighted inputs. So that's our concept, first of all. And now we have to turn this into equation at the end because we want to write a code. And so we have our inputs, I, and then we have our corresponding weights, W. And every input has to be weighted with this weight, so multiplied by this weight. And then we just sum up the result. So we have an equation that looks like this. We multiply these inputs with the corresponding weights W, and then we also add another constant or another quantity B, which is an internal quantity in the neuron, which is called bias. And I think the equivalent, the biological equivalent, is the so-called base potential. That's where it comes from. And also the bias can be adjusted during this learning process in order to have the optimal output. So our equation is just the sum of the weighted inputs with the different weights W, and at the end we just add a bias B. So the result will be just a number. But what you see here is the structure of a dot product. So this is actually a dot product. So we can actually picture that as two vectors, the vector I with all the inputs and the vector W with all the weights. And then we just multiply them like a dot product, which is just a scalar. So we'll just have a number, and then we add the bias B, which creates an output, and the output is also just a number. So that's first of all our concept. And now we can already start to turn this into code. And how would we do that? So let's first of all set up a function that we call single neuron. So we just want to create a single neuron that just computes this equation that you see here on the right-hand side. Of course, it requires an input, and we need NumPy as a library, and it has to return an output because we also want to check the structure of the output, whether it has the correct shape, for example, and the correct orientation of a vector of a matrix. And we can have, so this vector of inputs can have a particular length, so we can have I different inputs. So first of all, we want to determine how long this vector is, what the length of this vector is, because then we also know how many weights W we are going to need. And we will want to start, first of all, with random numbers. In fact, in the neural network, you initialize these weights with random numbers and then adjust them during the learning process. So we want to create these weights first with a random number generator. And we want to create a vector that has one row and L columns. So for every input, we have a corresponding weight W. And then we also create with a random number generator, generate the bias, and this is just a 1 times 1 matrix. And of course, we have to multiply the weights of the bias. It's just a dot product, as I said earlier. The weights of the input, sorry, it's just a dot product, and then we add the bias, and then we have our output. And of course, we want to run and save the code and run the code. So therefore, I would now just switch to my Python user interface. And in my case, I'm using Spider. And of course, you can use any other interface, what you like. But I prefer Spider because we will also see the variables here and the variable explorer. And I also want to create a few plots so that we can also take a look at these plots. And what I usually do is that I create a work folder. And in this work folder, I create subfolders according to different chapters, because we want to start with a very simple code, but improve the code continuously and add more functions to the code step by step, so that at the end we have a package. But for every step, we have these different chapters, and we kind of want to keep track of our progress. That's what I really want to recommend, to set up these different folders accordingly, so according to different chapters. So you don't have to do that, but I'm going to do that, and that's just my recommendation. So the first subfolder will be named in Single Neuron, and that's the first chapter. And we also want to navigate to our folder so that everything is in line. So let's now also create our function. So first of all, we import NumPy, and then we set up our function. So let's call it Single Neuron, and it requires some inputs. And once we have the inputs, it's determined the length of the vector. It's called inputs. And then based on this, we are generating the weights. One times L. And also based on this, we're generating the bias. So the bias is just one number. So it's 1 times 1, and then we generate the output by just applying the dot product with NB dot, and where we just multiply the weights with the input. And just add the bias. By the way, I just keep everything in line here, not because it's sensitive to the spaces, just the code, that the code looks neat and clean, and which really helps for keeping the overview of all the code and all the commands. And also we want to return our output and see what we get. So let us now first of all save this function in our folder. So just to make sure that it's all at the right place. So we go back to the folder Single Neuron, save it, yeah, then we have our neuron. So let us first of all create our input. So that can be just input with any arbitrary set of numbers. So we just want to check whether our single neuron works. And of course, we have to compile it. So let me then just run single neuron. Then we feed in our input I, and it generates an output out, and that should be just a number. And in fact, we just get a number. An output has the shape 1 by 1, the exact way as we want it to be. So our single neuron works, and now we can actually go back to our PowerPoint and see how we can perform the next step. So we have our single neuron. We have an input vector. We feed this input vector into our function that's called single neuron, and it creates an output. So it's just one number. So that's our code, and it's pretty simple. And we have a single neuron. But of course, a network has not only many neurons, it also has many layers of many neurons. So we should expand our code and write the code for more than one neuron. So let's say, for example, 3 neurons. That would be already one layer. So let's call it 3 neurons, 1 layer. And how would we do that? How would we actually change that? So first of all, we would change these numbers here. So that would be 3. And why is it 3? So let's take a look at those weights. So we have just one input vector with all these different inputs, but it's just one vector. And in the previous code, we just multiply this with the weights and we just got the number. So we just computed this equation here. But now we have 3 different neurons, so we have to do this 3 times. So if we have our input and multiply this with the weights, we have now 3 different neurons, and they're all independent from each other. So we just multiply input with the weights, and that generates a number, and we just do this 3 times. So what we will have as a result is a vector which has 3 rows in one column. So again, these weights are standing for these different neurons. So we have 3 different rows. That means 3 different neurons. And then we have these columns which correspond to the length of the input vector. So we have 3 neurons, and here we have our weights for every neuron. So the only thing that we need to change now is this number here, and the output then should be a 3 times 1 vector. And of course, we want to test this. However, we have to be careful with this operation here, so that because all these vectors and later also matrices have to be in the right orientation and have to multiply it also in the right way. So we have to keep track a bit of the orientation of those vectors and also of the shape. And I also want to do that. And I also kind of want to show you what can go wrong potentially. So that's the next step. So let's create now a layer with 3 neurons. And therefore, let's go back to our user interface, to Spider in my case. And in principle, we can just copy and paste this here and create a new function. And we just call this 3 neurons, 1 layer. All right, so we have now those L weights, but now 3 times. And therefore, we also have 3 biases. And we want to save this function. And of course, we want to run it. So let's compile this function. And let me make some space here. And Then we have our input and should return a 3 times 1 vector. So we have now 3 neurons. And we feed in the input and it should get us an output. And let's see what we get. So here's our output from the previous function. That's 1 by 1. And now let's take a look at the output. What happens if I run this function? It's 3 times 3. So it's actually not what we wanted. So why is that? So first of all, our input, and that's something that's particular for Python, is actually not a numerical array. It's actually a list. So that's pretty unusual for those who maybe come from other programming languages like MATLAB or Octave. So we should always make sure that we actually turn this into an array, and that's what we're going to do now. So we just want to do this with NumPy. So we change this to array. By the way, this is a bug here in Spider. So we turn this into a NumPy array. Of course, those numbers didn't change. However, if I now look at the shape of this array, it's 4 times nothing. And that's also one thing that's very particular for Python. And you probably might not be used to it if you're coming from another programming language, but we can also reshape this. There's actually a reason for that. I will explain the intro course. But now let's just ignore it and so on. Just say, okay, we have to change this a bit and have to reshape this. So we just use reshape. Again, here's just a little bug. We're just going to ignore. And we reshape this to length I times 1. And let's also take a look at the shape. So it has the shape that we wanted to have. And now let's run it again. So we just go back. And now let's take a look at our output. So it's 3 times 3. That doesn't make sense. But now we just rearranged our input array. So it's an actual array now. That's what you also can see here. It's not a list anymore. It's an actual array like the output. And in Python, there are different operations you can do with a list that you cannot do with an array. So therefore, it makes sense actually to turn into an array. So they generate the output, and it turns out now it has the correct shape. So we can also check it again. It's 3 times 1. So, and now we actually know how to create n neurons. And we don't need to stick to 3 neurons, and we can copy and paste this and perform the next step. So we create a new function, and then we just call it n neurons. So n neurons, 1 layer. How would we do that? So the thing was that n was just determined by the size of the matrix here. So we can actually introduce another input variable, n underscore neurons, which is the number of neurons. And then we are completely free with the number of neurons. So we can just have as many neurons as we want. So we have now a new function, n neurons, 1 layer. And also would like to save this function now. In the same chapter. And we also want to run this function. So what should happen now? So if we have just 1 input, all right, so just 1 input vector as we have here, and we have n neurons, whatever n is, our output vector should have the same length as n. So let's try that. So we again create our output, and now we just call this function n neurons, 1 layer. So the input is I, and neurons, let's say 10, for example. Why not? then this function is not defined. So let me just check. Well, it's also one thing that can actually happen. It's probably a typo. Let me just. All right, so it just was a typo, and let me run it again. So now we just have the number of neurons as 10, and of course our output is then also the length 10. So for every neuron now we have a contribution to the output, and every neuron now generates this output based on the same input. And of course, we're still working with random numbers, and there's still no learning process. So let me just go back to our PowerPoint then. So we just created this particular function. Then we also were checking for the orientation and also for the shape of the vector. We were also expanding this function to n neurons. So the problem, however, is that the input itself is actually a matrix. So we only had one input now, and this input had 4 entries. So it's a 4-dimensional input. So just think about a data point in 4D. And of course, you can have ND, but it's just one data point. Of course, in practice, you have many different data points, and these dimensions are usually called features. So if you want to plot it in a 2D diagram, then you have only 2 features, but if you have 4D data, then it has 4 features and so on. And you can have many different data points. So instead of having one vector, you actually have a matrix. And for each entry, so to say, you have to feed into the network, and then you generate an output. And of course, this output has to be the input of the next layer, because what you actually want to have is a real network, so that they have many different layers, and you just pass on the information from one layer to the next layer. So therefore, we have to learn how to create many different layers, and this is going to be the topic for the next section.